Hi, today's lesson is on average atomic mass. In a previous lesson, we learned that the majority of an atom's mass comes from its nucleus. The majority of an atom's mass comes from the nucleus. And we referred to that as the mass number. From another previous lesson, we learned that atoms make up elements or comprise elements. And we know that isotopes are atoms of an element with different masses. Let's elaborate. The number of protons are the same, but the number of neutrons are different. So in other words, if we're talking about the element carbon, it's made up of carbon atoms, and if I wanted to know how much the mass of the element is, one would argue that I could figure out what the mass of all the atoms are and take the average of all the atoms, and that would get me the overall mass. So if we've got the average mass of the atoms, that would give us the overall mass of the element. Let's work through the math using an analogy, where instead of talking about the element carbon, we're going to talk about the element M&Ms. So if I were to have a pile of carbon sitting on a balance, and I was able to pick out the smallest pieces, I'd be picking out atoms of carbon, or carbon atoms. Just like in our analogy, if I were to have this element called M&Ms, and I were to reach into the bag, I would be picking out candies or pieces of M&M, and these are meant to represent the atoms of the element M&M. Hopefully you're with me so far. Let's hypothetically say that the mass of the red M&M is 1 AMU. AMU stands for atomic mass unit. That's where the AMU comes from. And it's a totally made up unit to try to get this abstract concept to make sense to what we see in the real world. So for example, if I were to say that one red piece of candy weighed 1 gram, if I'm trying to make that analogy by saying it's an atom, that's absolutely ridiculous, because a gram in real life is about the mass of a paperclip, and there are tons of atoms that make up that paperclip. So the size of one atom, the mass of one atom, has to be so significantly small that it's almost immeasurable. Hence why we use this made-up unit, totally imaginary, called AMU. Let's hypothetically say that the yellow M&M candy, or the yellow atom, weighs 2 AMU. The green weighs 3 AMU. The blue weighs 4 AMU. The orange weighs 5. And the brown weighs 6. So coming back to the analogy, what we have here is an element called M&Ms. And we know that atoms make up elements. The atoms of this element M&M are orange, yellow, green, blue, red, orange, and brown. We know that isotopes are atoms of an element with different masses. So these are all these different colored candies are all atoms of the same element. What makes one different from the other, in real life it's color. In our analogy, it's going to be mass. So if I now come back to the concept that we're trying to get across here, if I want to find out what the mass of an element is, I should take what the average mass of all the atoms are. So based upon this idea, or this analogy, if I wanted to find out what is the, if I wanted to find out what the mass of the element M&M is, I would take the average of what the masses of the atoms are. I've got 1 AMU, 2 AMUs, 3 AMUs, 4 AMUs, 5 AMUs, 6 AMUs, right? And I'm going to add them all up together. Those numbers come from the mass of each isotope of M&M. And then to take an average, you divide it by however many pieces there are. So there are 6 pieces. All right, so doing my math, that would give me a value of 3.5 AMUs. All right, let's see if that concept holds true as I look at these other samples. So that was me reaching into the bag and picking out the candies one by one by one. But now I pour some into a bowl. And when I look here, I can see that there are 2 red in this bowl. And I know that my reds weigh 1 AMU. And I can count 7 blue. The blues weigh 4 AMUs. I count 3 yellows. Each of them weigh 2 AMU. I count 4 orange candies, or atoms, and the orange candies weighed 5 AMU. I can see 2 brown candies, or atoms. They weigh 6 AMU. And I can see 1 green. They weigh 3 AMUs each. All right, so let me go ahead and continue the concept here. If I wanted to find out what the mass of the element is, I need to find out the mass of all the individual candies in this sample and add them up together. So I've got 2 reds. I've got 7 blues. I've got 3 yellows. I've got 4 orange. I've got 2 brown. And I've got 1 green. According to averages, you have to divide that by the total number of pieces. And there are 19 pieces of candy in this bowl. So if I go through and I do all my math, 2 times 1 is 2, 7 times 4 is 28, and so on down the list. All that divided by 19. Adding that together, 75 divided by 19. My mass winds up being 3.9 AMU. That's not what we got up here before. This is a higher value. Interesting. Let's try one more example. Let's try a larger sample. So I've got another bowl here. I'm going to go through the same idea I'm counting all the pieces, and then I'm going to figure out how much does the whole element weigh. So we wind up having 16 greens and 25 blue and 20 orange pieces and 21 brown pieces and 11 yellow pieces and 10 red ones. And again, we're trying to come up with the average. So I now need to divide this by the total number of pieces. And there are 103 pieces in this sample, in this dish. All right, so hopefully you trust my math. Multiplying and adding all of that up together, we get 406 AMUs divided by 103 pieces. The mass winds up being 3.9 AMUs again. So we got that number twice. So, well, where's our real answer? Which one is the best analogy for looking back at our original example? The mass of the carbon element compared to the average mass of the atoms. Well, in real life, what happens is more of what gets dumped in the bowl. Right? If you wanted to figure out the mass of the candy M&M, you're going to have to account for all the candies in the bag, not just one of each. In other words, the relative atomic mass of an element is the average value for the isotopes. However, it has to take into account the percentage of abundance of the isotopes. And this is really how we go about calculating the average mass of an element. What we did in these last two calculations about the M&Ms in the dish, that was based upon abundance. We stopped and we counted how many of each isotope of M&M was in our dish, and we took that into account when we did our calculations. That's the truth of how we use this analogy to go from atoms to the mass of our element. So take the time to read this again. The relative atomic mass, remember this is the average atomic mass. The average atomic mass of an element. It, again, just like we've been doing with our math, it's the average value for all the isotopes. So we're taking all the colored candies of M&Ms into account. But what we have to worry about is not just how much does each one weigh and then divide by 6. No. Just because there are 6 candies available to us does not automatically mean that they're going to be represented in the same quantity in each bag or in each dish. Hence, we have to take into account the percent abundance of the isotopes. Let's do a couple of examples together with real elements so that you get a better idea of what we're talking about. So we have, again, the same knowledge that we started with. Isotopes are atoms of the same element that have different number of neutrons. In other words, that accounts for the different number of masses. So if we look at the element of chlorine, it has 2 isotopes, chlorine 35 and chlorine 37. Chlorine will always have 17 protons in its nucleus. The difference is how many neutrons there are. We're focusing again on the mass number. The mass of an atom is told by its nucleus. The nucleus contains protons and neutrons together, so we focus in on the mass of the nucleus. Now, when you look at the abundance, percent means out of 100. So 75 out of 100 atoms are going to have the mass of 35, and 25 out of 100 atoms are going to have the mass of 37. So how do I now figure out what the average is? Well, we're basically doing our math here. We take the mass number, giving you like a formula for how you can do this calculation. You take the mass number, and you're going to multiply by, this here is the percent abundance, and you're going to do that math for every single isotope that exists. So again, we've got our mass number times the percent abundance and then with all averages we have to divide by 100, and that'll get us the mass of the element. So looking at the math that I've got up here, 35 times 75 divided by 100 plus 37 times 25 divided by 100 equals 35.5 AMUs. Now hopefully that makes sense to you. Let's go back to our M&Ms for a second. If I really had equal numbers in my sample of every single color of the M&M candy, I should get an average mass of 3.5 atomic mass units. But in my two examples, I wound up with values that were greater than the average. Why? Well, it's because my samples had more atoms that were heavy compared to atoms that were less. So it's going to be higher than the average value. Let's look at this example for chlorine. 75% of the times, the average is 35. 25% of the time, the average is 37. If this was a 50-50 split, the average atomic mass would be 36, because that's the average of 35 plus 37 divided by 2, right? That's 50-50. That would be half. But when you look at the actual answer of 35.5, it's not exactly halfway, because we're not in 50-50 percentage. We've got way more of the isotope that weighs 35, so our average is going to be closer to the 35 mass rather than the 37 mass. Let's use that logic looking at the data for carbon. Carbon has 3 isotopes, carbon-12, carbon-13, carbon-14. In terms of the abundance, 98.892% of the time, the carbon-12 isotope exists. 1.108% of the time, the carbon-13 atom exists. And 2 times 10 to the negative 10th percent, that's really small, the carbon-14 atom exists. So when you take all of that into account, just logically, which of these masses should our average come closest to? You're gosh darn right. Our average should come out to 12. And if you take the time to do the math, we should come up with the number 12.01 AMU. And that's really close to 12 because we've got almost 100% of the time the carbon-12 isotope is the one that's going to exist. Let's do one more practice problem together working through the math, and we'll do it with strontium. Strontium has 4 isotopes, strontium-84, strontium-86, strontium-87, and strontium-88. You've been given the actual data for how much those isotopes mass. Therefore, this is the data that you should be using in your calculation, despite the fact that the mass numbers are given to you here. So if you've got enough scientific data that gives you what the actual mass of the atom is, that's the data you'll work with in your calculation. And then you'll take into account the percent abundance. So when it comes to strontium, if you wanted to think of it in terms of an equation, we're going to have 4 different pieces of data that we're adding together because we've got 4 different isotopes. So in that first scenario here, we're going to take what the mass is, 83.913428, and I'm going to multiply it by the abundance. Now, a lot of you, when you think about the math we just did up here before, say to yourselves, well, can't I just do this fraction first? Can't I do 75 divided by 100, change it to a decimal, and be done? Absolutely yes. Just don't divide again by 100. If you're going to take the percentage and change it into a decimal, you're already doing your division. So don't do it again. So you'll multiply this by, oopsie daisies, 0.0056. and I'll add to that the second isotope's mass, 85.909273, and I'll times it by its abundance, 0.0986. I will add to that, let me move down here, the third mass isotope, 86.908902, times its abundance, 7% converts to 0.0700, and the last isotope, 87.905625, multiply it by the abundance, 0.8258. Now again, just checking logically, the percent abundance of 82.58% of the time, our average should be closer to the 87.9 rather than the 83.9, because we've got such a relative abundance up here, a high one. All right, take the time to crunch the numbers. When you multiply those first two numbers together, we get 0.47. And then the next set, we get 8.47. And then a 6.08 and a 72.59. Adding all of those up together, we wind up with 87.61 AMUs. And that is the average atomic mass for the element strontium. Thanks for watching.